All right, so here's for electricity and circuits, this particular unit. And first one is an example from the openstax textbook, 18.1, so that's already worked out, and here it is. In just one moment, I think I'm going to make this a little bit bigger. Nah, I decided I'm just going to leave it like this. So, how strong is the Coulomb force relative to the gravitational force? In an example, they're using an electron and a proton, which are separated by this tiny distance, 10 to the negative 10 meters. So they're very close, hence the attractive force, in this case of the Coulomb force, should be pretty strong, and so should be gravitation because they're pretty close. But of course, they have very small charges and they have very small masses. So here we're going through the motions of figuring out what the force is, the electrostatic force, the Coulomb force between the two. Here's the Coulomb constant, 8.99 times 10 to the 9. Then here the charges, electron and proton, have the same charge, 1.6 10 to the negative 19. And then there's the distance that is given in the problem. And I figured I might as well show this here, how to compute that. So let's see, 8.99. 10 to the negative, no, 10 to the 9th times parentheses 1.60, and you know, if you put in, is it 02 or is it 09? One of the two. It's actually 02, so if you put the 2 there or not, doesn't really matter. E, or 10 to the negative 19, so here's very small, and because they have the same charge, the proton and the electron, I simply square that, and then I divide by, I'm going to put this in parentheses, the 0.530, 10 to the negative 10. There we go, parentheses, and that has to be squared as well, Coulomb Law, enter, and there it is. That's what they, of course, show us, the 8.19, 10 to the negative 8. Okay, then they do the same thing for gravitation, and I spare you plugging that in. Basically the same thing. Of course, now we have the masses and the gravitational constant, which is really small. And this is actually kind of the kicker here. Oops. The gravitational constant is really tiny, 10 to the negative 11, while the Coulomb constant is actually relatively large, 10 to the 9th. So that's a big difference here. The masses are really, really tiny. The electron, 9.11. 10 to the negative 31, and the other one is 1.67, 10 to the negative 27. The proton, which is about 1,836 times larger than the electron. Some numbers I have memorized, some numbers I approximate in my head. And then we come up with this super tiny force between the two, even though they're very close, 3.61, 10 to the negative 47. And now if we compare them, and basically you just have to compare the exponents, 10 to the negative 47 to 10 to the negative 8, which is 10 to the 39. And here it is, which means that the Coulomb force is, well, 2.27 in this case, times 10 to the negative 39 larger than the gravitational force. And here it says this is a remarkably large ratio. Note that this will be the ratio of electrostatic force and so on, which is also the thing that the Coulomb force between charges, so the electrostatic force, is very huge compared to gravitation. But the thing is, most of the stuff that we have around us is electrically neutral, because for each proton that we have, there is actually an electron. So we're made out of gazillions of protons and neutrons, and we're made out of the same gazillions, the same number of gazillions of electrons. And so those charges totally cancel out, and you rarely do you have some charge left over, unless, of course, you go to the outlet, and then, yes, there is a lot of charge there, and you can really, electricity, when you have large charges, can be dangerous. And on the other hand, if you want to keep it safe, we use electricity all the time. Just on a large scale, or on a normal scale, gravitation is we can feel it much more, because we do have masses, they always attract each other. But again, Coulomb force, positive charges are almost always canceled with the negative charges that are around. Okay, I made an example myself here for this, and I call it Earth and Moon. I have this on a prep slide, which if I was teaching this class in person or on Zoom, then you would actually see that. So I did this calculation here. I think my two blue dots here might be just the distance between two charges or masses. I wrote down the same Coulomb's law and the gravitational law. How strong is the electric force compared to the gravitational force? And I say very strong. What mass of electrons must be transferred to the moon to keep it in orbit without gravitation? That's the question I ask myself. How come we don't feel the electric force as much as we feel gravity? And I just explained that question, actually. Here, I'm going to come up the gravitational force, where to go, is about between the Earth and the Moon. Oh gosh, I can't read my own thing here. 46, 45, 60, 46, 30. Yeah, I think this is 10 to the 20 newtons. So 10 to the 20 newton is the gravitational force between the Earth and the Moon. And now I'm computing the charge of electrons that I would have to get to the Moon in order for there to be the same attraction. So I set that equal to the Coulomb force. So my example here is not comparing the gravitational with the Coulomb force, but getting something else out of it. I already know that the ratio is 10 to the 39 power or times. So I set this equal here, and I compute the charge out of this here by eventually taking the square root. There is the distance between the two, between Earth and Moon is 380 million meters or 380,000 kilometers. And here the mass is 10 to the 24 for the Earth, 10 to the 22nd for the Moon. By the way, the Earth over here and the Moon over there, that's about the correct size for their for their size, but the distance is not correct. The Moon would have to be way further out. I think in the neighborhood of like another 20 feet or so. That should be away in the scale here. Anyway, I compute the charge, and this is what I come up with here. The charge that needs to be transported over there would be 5.7 times 10 to the 13 coulombs. Okay, that seems to be a lot of charge, 10 to the 13 coulombs. Okay. How many electrons? Well, I divide by the electron charge, which is 10 to the 32 electrons. That's a lot of electrons, yes. Now I'm going to determine the mass, and here comes the interesting thing. So I multiply by that very tiny mass, and I come up with 325 kilograms, which is 714 pounds, as it says here. So in order to get the same gravitational attraction between the Earth and the Moon as a gravitation, all I would have to do is get 700 pounds of pure electrons from the Earth to the Moon. And then, of course, that leaves the same amount of charge behind, the 5.7 10 to the 13 coulombs as positive charges behind. And now the attraction between the two is exactly the same as gravitation. And that is how strong the Coulomb force is. Just a small amount of electrons, 700 pounds. It's not that much. But that is enough, if it's pure electrons, to be attracted by the positive charges that are left behind on Earth. Okay, and I think I'm finally done with this problem. All right, so here's the next problem. So this is from the OpenStax textbook, Chapter 18, Problem 10, pith balls. What is the repulsive force between two pith balls that are 8 centimeters apart and have both the equal charges of negative 30.0 nanocoulombs? That's pretty small charge, nanocoulombs. What's a pith ball? I guess, let's see. There we go. And here we go. So there we go. Pith balls are little styrofoam or similar material balls coated in conductive paint. When charge is brought closer to pith balls, their charge is polarized, and so on. So that's a pith ball. I used that term for a long time. It's kind of like a funny physics term to use that. Anyway, so here's the calculation again, Coulomb's law, and if I do that, I'm going to clear this one out. I'm going to do second entry and watch, because I already have the Coulomb's law. I don't need to retype the constant there, the Coulomb constant. So this one is going to be, now this is the charge, is the 0.010 to the negative 9 in this case, divide by, and these are much further apart, so this one is 0.0800, and I get rid of the rest, and if I didn't make a mistake, I come up with this. Let's see if that's true. Oh, yep, there it is. So 0.00126 newtons. They wrote, not sure how they, look, they rounded strangely, right? They should have rounded 1.26 10 to negative 30 newtons. Anyway, relatively small force. Okay, that can also be determined experimentally with this experiment, and notice the original one here I got from the other physics book, Cottonell and Johnson, so also chapter 18, and there it's number 23. And so here you have these two pith balls hanging on strings, kind of like you have over here. And now you apply Newton's second law to it. For some reason, I should have written here first, sum of the forces equals mass times acceleration. Since nothing is moving, the acceleration is actually 0, hence you see a 0 here. And then I already split it up into its components. So in the X component, you have the Coulomb force, which in this case is repulsive because they're both negatively charged. Oh, by the way, in my computation earlier, I really didn't need the negative there, right there, because it was squared anyway. So the negative, I got rid of the negative anyway. And so here's the Coulomb force in the horizontal and the cosine of the tension in the string. And then in the y direction, I have gravity and the sine of the tension. And then I do a bunch of algebra here and I come up with this. And then I compute at the end. Okay, 1.7 10 to the negative 8 coulombs, which is 17 nanocoulombs. So really similar result to what we had earlier. And the original problem in this case, you asked for how many electrons. So I divide by 1.6 10 to the negative 19. I come up with 10 to the 1100 billion electrons. Okay. Then I looked up, besides the pith ball, I did find, I'm going to turn this one off, styrofoam ball. Don't know what that word meant. So he takes a rod and rubs it on a cat fur. And the reason I'm laughing at this is because when you go to a physics lab, you will find a bunch of electrostatic stuffs like these rods or styrofoam plates or what have you in these pith balls. And you will find, and I'm not kidding, rabbit fur and cat fur. So I think it's kind of neat that they had a live cat in this one here, and charging the pith ball and showing the attraction then in this case. I want to cancel this one here and show you the other one. So here, let's see. Whoa, this is really big. And starts at beginning here. Anyway. So here are these two pith balls, and this person actually is either using a piece of cloth or actually a cat or a rabbit fur. And there's a difference between the two. Now here he has two pith balls, or she, and is charging these two pith balls with the same kind of rod. So the rod has, let's say, acquired negative charges. It gives them both to both pith balls, and therefore, of course, they do repel each other. And yes, you could determine the angle here, and you can determine then the Coulomb force and the tension and gravity, put them on the scale and figure out the same thing, how many electrons were transferred and how many, here he or she just shows that they're repelled by the, no, actually they're attracted by the other rod, I think. So you could do the same computation, coming up with number of electrons and the amount of charge. Okay, that's what I think I finally had with this problem. All right, this particular one, transparent tape dispenser, I just show you the solution here. Again, it's Coulomb Law, and it says something about picking up a piece of paper somewhere, top piece's weight, after the transparent tape that you have taken off, pulled off from the dispenser, becomes charged in the process due to friction, and then you put it on something else without the glue actually, and because of the charge that you have on there, it will actually be able to support a small amount of mass. It says 10 milligrams piece of tape. I'm not exactly sure. Calculated magnet of the charge is great enough to support the weight, held 1.0 centimeters above another. I think you have to hold them at top of each other without them becoming too close, because otherwise the glue takes over, right? So they do use the Coulomb law, and then mass times gravity. They plug in the numbers. It's very small distance, hence 0.01 meters. The mass is really small. It says 10 milligrams, so 10 times 10 to the negative 6 kilograms. Did I say 10 milligrams? That's what I meant. That's, I think, is what I said. So very small in kilograms. And then there's the Coulomb constant, there's gravity, and you come up with 1 nanocoulomb, which I just showed in the case of the pith ball. That's actually true. So yeah, very small amount of charge. All right, so this problem, by the way, I'm doing this recording here for Unit 2, which is electrostatics and circuits, after I did Unit 3 for electrodynamics. And you will see when I do that in electrodynamics, I have to fill myself, because there we're going to get three-dimensional, and there are 2 right hand rules, and I have to fill myself. And that was quite an involvement to do that. You will see that when you get to Unit 3 what I did there. This one is a whole lot easier because I don't have to fill myself, so it's just looking at these problems here. Okay, so a 5-gram charged insulating ball hangs on this long string in a uniform horizontal electric field, as shown in this figure. Given the charge of the ball is 1 microcoulomb, find the strength of the field. And what I should show is actually the original problem. It has that figure in it, so didn't prep that one, but it shouldn't be very hard for me to find. So, and let's see, problem 60, there it is. So this is the original one, and then it says 8 degrees here, and here is, so it's similar to the pith ball that we had a moment ago. It's a whole lot heavier, I guess, 5 grams. But here we simply have a uniform electric field, which is produced by some kind of source that produces that electric field. So here it is. I guess the angle is totally exaggerated in this case. I don't like in this particular problem that they use the capital T for tension. I would use FT, force due to tension. That's what I would do. And then FE here, well, that's kind of like, well, that would be the Coulomb force, but it does make sense to call it the force due to the electric field. And you find this equation in the book. Charge times electric field. That would be in the horizontal direction. Notice that they take the angle from the vertical theta, and therefore the sign right here actually appears in the horizontal, which again I don't like, so I would have written this somewhat different. Overall, it would be actually, the algebra would be exactly the same. I just would have used different symbols and swapped the cosine and the sine and the angle and so on. In the vertical, well, you have the tension in the vertical that is going up, and gravity, and then all these 4 force components. Actually, there are only 3 forces. Again, if I go back here, you can see that the electric field toward the right pushing it out, tension to the upper left, and gravity pulling down. So 3 forces, but 4 force component, because the tension splits up into horizontal and vertical. And then you do a little bit of algebra, and that's what you come up with. And again, if I use the calculator here, I'm going to put this over here. There we go. This might work. So 5, 10 to the negative 3. I guess I could have put 0.05 there, times 9.8. The calculator really doesn't care about significant figures. I do, yeah. Tangent of 8. So I could type the 8.00 there, but again, the calculator doesn't care. Times 1, divide by 1, 10 to the negative 6. And before I do that, I'm going to go to mode. I'm going to check if I'm in degrees or radians. I am in degrees, which is what I need. In physics, we always use degrees. Well, not always, but for the most part, we use degrees rather than radians. Hit enter, and yes, I do come up with around at 6,900 newtons, and that's what they say there, 6.89, 10 to the third. Oh, Newton per Coulomb, because they were determining the electric field. All right, I'm actually going to give myself a break here before I do the next problem. So here's a little afterthought for the pith balls that are repelling each other, or the tape dispenser, how much charge there's on there, and you will see that in this particular one. It comes really close. So this one is called a collection of solved problems in physics, and you can see the web address up there. And here it is, two small balls with this kind of mass are hanging on separate strings, 1 meter long, attached to a common point. They're given an identical charge and spread apart to a distance 4 centimeters from each other. And then there's a hint. What are the forces acting on the balls? What is their direction? Draw a picture. I'm not sure why the analysis is first before the figure. Here's the figure. So there we go. So this is how it is. By the way, this is totally exaggerated because it already said that this one is 1 meter long, 100 centimeters, while this one here is only 4 centimeters total, I think. So 2 centimeters compared to 100 centimeters. It'll become important in the analysis, by the way. Here are the forces. You have the tension in the string that is holding up the balls. Then there's the Coulomb force that repels them. And then, of course, there's the weight pulling them down. And each one of them gives us a nice Newton's second law. Sum of the forces equals 0. And that's what they're figuring out in the analysis and solution. I guess here, this is just a diagram for looking at the particular sides here, so the length L and then the vertical V and the angle alpha and so on and so on. All right, gonna go to solution. Here's the Coulomb Law. Then at some point, let's see, they're going a little bit quickly. They should really write down actually here Coulomb Law plus gravity, and then that should equal, or plus tension, and that should equal all 0. So they should go a little bit slower here, and yes, eventually you come up with a tangent of the angle is this one here, and then you're going to come across the Pythagorean theorem. By the way, this one isn't necessarily needed. Watch this. I'm going to go back to the diagram. If this is really long, and it says 100 centimeters, and this one is really short, it says 2 centimeters, then the adjacent here, the vertical, is basically the hypotenuse. So if this is 100 centimeters, then this is basically 99.5 centimeters, something like that. In any case, we actually don't necessarily need this one here because it's basically the same thing. So I would just leave that out. So here, down here, I would just say, hey, that's L or 2L. And then here, plugging in the numbers that are given in the problem, and at the end, you're going to come up with this. And the 4.2 nanocoulombs is basically in the neighborhood of what we determined earlier for the tape dispenser and the pith balls. And I'm not sure why there's an answer now. There's the answer again, 4.2 nanocoulombs. As I said, it was a little bit of an afterthought here, and introduce you to this website here that does at least a number of solved problems in physics. All right. All right, so here's the next problem. So this figure here shows an electron passing between two charged metal plates that create this much of an electric field perpendicular to the electron's original horizontal velocity. So the electron is being deflected, in this case upward. The electron is negative, going to the right. The positive charges are on top of this electric field, so it will be deflected upward. And the red part, actually the red part to approximately here, they say neglect any side effects, so approximately here, that is actually a parabolic path, and I guess it starts out very slow and then it gets steeper. So this part here is actually all parabolic, and then once it leaves the electric field, well, because of its inertia, it's simply going to go straight out. So you have a continuation of the parabola with a straight line. All right, the numbers are given here, and the electron is here, so I'm going to go over here, and there's the same kind of diagram, and then there's a whole bunch of algebra, and notice that the algebra, wow, this is a lot here, so I'm just going to try to take it apart. They start with Newton's second law, so force equals mass times acceleration, and they say, okay, the force that we actually have is the charge times the electric field. Let's figure out what the acceleration is. Unfortunately, they don't do that right here. They actually plug that in, the QE divided by m, but I'm going to do it here. So it's going to be a tremendous acceleration. So let's see, the charge of the electron, 1.60 10 to the, oops, I meant to say, there we go, 10 to the negative 19, that's a charge of the electron. Then I think it did say 100 Newton per Coulomb, so times 100. And then I divide by the mass of the electron, which of course is very tiny, and that will give me the huge acceleration that I just mentioned. So here we have 1.7, so oops, gone, 1.756 10 to the 13. So AY in the vertical direction equals, what was it again? 1.756 times 10 to the 13 meters per second squared. Let me just double check. Yes, that looks right. Okay, next step to do, and by the way, this is AY. Word, of course, wants to give me a capital A there. So anyway, I'm going to change it there, AY, and if it really, I'm just going to leave it like that. Oh, that one here, I do want to put it as an exponent there. There we go, it looks a little better. So huge acceleration, but it's not in there for a long time, which is what they're going to calculate next here. So here they take the length divided by the original velocity. So the length of this one here is given as 4 centimeters, and the original velocity already is pretty large, 3 million meters per second, roughly 1% the speed of light. So compared to light, it's very slow, but compared to anything else we're encountering, it's pretty darn fast. 3,000 kilometers per second. That electron would race through the Earth's diameter in about 2 seconds. No, actually 4 seconds, because the Earth's diameter is 12,000 kilometers. Any case, so divide these two numbers by each other. So basically, how much was it again? 4 centimeters. Okay, so basically 0.04 divided by that huge speed there, 3 times 10 to the 6th, and I come up with, what was it again? 1.33 10 to the negative 8. So the time that it takes to go through is 1.333 times 10 to the negative 8 seconds. There we go. And here we go, exponent. All right. Then with that, they're going to figure out, okay, this is going to be the distance it's being deflected upwards. Apparently they come up with 1.56 10 to the negative 3 meters. So very small. That's about 1 millimeter. So even though it has this tremendous speed at the end, when it or acceleration, and this tremendous acceleration, but it doesn't have much time to apply that, so its deflection is very little. They simply use, we are familiar with that. When you accelerate something like that, it goes all the way back to one of the first chapters in physics. The distance equals 1/2 acceleration times time squared. There it is. So I'm just going to plug in my numbers here, and we should come up with the same thing, 1.56 10 to the negative 3. So there we go. Oh, the two numbers are actually still on here on the calculator. So it's going to be 1/2 times the acceleration that I had earlier, which is the 1.756 10 to the 13 times time squared. Here's what I'm going to do, parentheses. I already have the answer there, so I just do that. Hit answer on my ch.18, parentheses, don't forget the square, there it is, enter, and true enough, 0.0156 meters is what I'm going to come up with. So basically, I did do the same calculation they do here. I just split it up a little bit because I think what I just did looks a little nicer. So what I have, 0.0156 meters is the deflection. I'm going to give myself a little break here and look at the next part that I want to do. All right, I checked it out. So I'm supposed to come up with these 234,000 meters per second, so also a very large speed in the y direction now that it has acquired through the electric field. Notice all this algebra here? Well, because I split up my problem, I already know what AT is, and this is a typical kinematics equation. The velocity in the y is the original velocity in the y, which actually doesn't exist because it goes through horizontal, plus AY times t. That's only why the A and the t survive. But I have these here, right there. They're in front of me. So I'm going to use the calculator over here. So let's see. I think I'm going to clear this out a little bit. Yeah, simply what I had earlier, the 1.756 10 to the 13 multiply by 1.333 10 to the negative 8. There we go. Hit the enter button, hopefully. And there we go. 234,000 meters per second, which is what they got. 234,000 meters per second. Okay, last part. I don't think I need to prep that. The last part for the angle is to use a little bit of trigonometry. So the angle here would be distance here and distance there and so on, or it could be the velocity in the x direction and the velocity in the y direction, and the relationship between them is the tangent of the angle. So here's what I'm going to do. It's the y angle, the y velocity divided by the x velocity. So I'm going to do the number actually that I have on the screen. So I simply divide the answer by the original given x velocity, that was 3 10 to the 6th. There we go. I come up with a relatively small number, 0.078, and I need to take the inverse sine of that. I'm sorry, the inverse tangent of that. There we go, the answer. And I come up with 4.46 degrees, which is exactly what they have here as well. Okay, and I think I'm done with this problem. All right, so here is the next problem for this chapter, last problem for this chapter, and I'm going to continue with the next chapter. So a classic Millikan oil drop experiment was the first to obtain an accurate measurement of the charge of an electron. Robert Andrews Millikan, got actually the Nobel Prize for that, for determining that charge of the electron very accurately. In that experiment, oil drops were suspended against the gravitational force by a vertical electric field. Given the oil drop to be this much in radius and have a density and so on, find the weight of the drop. If the drop has a single excess electron, find the electric field strength needed to balance its weight. So it is in a chamber here where you apply an electric field and you have control over that, and then you watch these oil drops with a microscope actually. So I found this video here, so let's watch here for a moment. I muted here. So this is actually, she really has to look through that microscope, and here is actually the oil drop suspended, and she has like this little thing here that puts vapor in it and oil drops, charged oil drops. And by the way, this is not evacuated. There's just normal air in there. And I'm going to go back here because so you can see it again what she's doing there. So they actually fall through the air. They're very lightweight, so they fall through the air actually very slowly due to their weight. They fall down, and then if you apply an electric field upward on them, you can actually counteract that. So I got this one here from GeoGebra, this applet here. So notice I have 0 voltage applied to it, and when I hit the run button, then it falls on the influence of gravity. And now the thing is, notice it's actually relatively slow, right? Negative 1.4 here, and it takes 5 seconds to fall down. But the thing is, you have to picture there's actually air in there. It's not in free fall. So the air resistance actually has slowed it down. If I reset, you will see the same thing. It does accelerate at first, but air resistance then slows it down to, gives it its terminal velocity. Now, if I apply a voltage here, so here we go, there we go. There's the electric field. Then actually you can see, the electric field now would pull it upward. You know, it's a negative charge, so I have a pause. Hold on. Actually, that one is a positive. Wait. This is a positive charge here on this oil drop, and hence because you see the positive plate there at the bottom. So, electrons are stripped off the oil drop. That makes total sense. Electrons are stripped off the oil drop, and now you have positive charges. And then you try to balance it, and you have to look through this microscope. So Robert Millikan and his grad students or whoever employed his assistants, they had to do a lot of minuscule work. I remember doing this 30-some years ago as a student. And yes, it was actually quite tedious to watch those oil drops and take measurements on them. Anyway, so that's the experiment. That's the premise. So I'm going to go back to the problem. Here we go. And I forgot to turn the GeoGebra off. Oh, no. There we go, pause. Oh, that's better. Whoever wants to watch that. Okay, so it wants us to find the weight of the drop. The weight is, of course, mass times gravity. Density times volume times gravity. There we go. Plug in all these numbers, and you come up with a very small amount of weight. Some of these are given, like the 1 micrometer in radius are given, and then the density of this oil is 920 kilograms meters per cubic meter, which means it has a density slightly less than water, hence oil floats on top of water. And then times gravity, and you come up with this really small weight for it. And then it asks, so 10 to the negative 14 newtons, and then it asks for if the drop has a single excess electron, which actually, as you noticed a moment ago, oh yeah, here you see it in the drawing, right? Positive charges are on top, negative charges are at the bottom. The GeoGebra one here actually was the other way around. So here the oil drop actually would have a positive charge as if it has an electron stripped off it. But still, it's absolutely the same concept, no matter how you do it. So here the electric field, therefore, is balancing the weight. So you have the electric field, therefore, is the weight divided by the charge. You plug in the small amount of weight by the tiny charge, and you come up with a relatively strong electric field of 236,000 newtons per Coulomb. And with that, I'm done with this problem. All right, so chapter 19, problem 10. Fusion probability is greatly enhanced when appropriate nuclei are brought close together, but mutual Coulomb repulsion must be overcome. This can be done using the kinetic energy of high temperature gas ions or by accelerating the nuclei toward one another. They keep talking about here any kind of nucleus. For fusion, really what you want to use is hydrogen because it's the lightest one, so you can get it actually the fastest. So you can actually get them close enough to fuse together. They just want to keep it in general here. Also notice that because they do keep it in general, there will be actually no mass involved for these computations that we're going to do. So anyway, calculate the potential energy of two singly charged nuclei separated by 10 to the negative 12 meters. I actually had to look that up. That's the attometer. Atto, A-T-T-O, by finding the voltage of one at that distance and multiplying by the charge of the other. And then at what temperature will atoms of a gas have an average kinetic energy equal to this needed electrical potential energy. And the text here is straight from the textbook. The two diagrams that I put in here, this would be the typical cycle of nuclear fusion inside the sun. And similar stars, and there's a variety of nuclear fusion cycles, but this is the most common one, which is called the proton chain. Notice that there's a total of 6 protons that are eventually fusing to become helium-4, and then 2 protons actually are being emitted from that reaction. And notice that these both are positively charged, and the electric repulsion is a huge, or electric force is a huge force, and so they really would just like to fly apart, but if you get them close enough, then it can actually be done. This one here is the typical cycle within a nuclear fusion reactor on Earth, and there's certain reasons for that. I tried to read up on it, couldn't figure it all out. I actually did quite a bit of studying, even though I teach this stuff in astronomy, for example. I teach it once a year in Physics 124, but I still had to look up quite a bit. So here, this particular thing, I didn't. Why is it tritium? Why is it deuterium, which are isotopes of hydrogen? And it has to do with that they're more or less easily available. Actually, hold on, this is actually deuterium. This already is. This is tritium, that's right. And then we get helium out of that, and we get a leftover neutron out of it. I think it's because they're readily available. So that's why they're rather used. And here you actually have to fuse 6 protons together. It's apparently easier if you just fuse 2 nuclei together in a nuclear reactor. The sun has a much higher probability of doing this one, and of course the core is really dense as well. Okay, let's just do the calculations, and that's actually going to be straightforward. So here I wrote down the Coulomb force again, the Coulomb constant times the 2 charges divided by the distance squared. The potential energy would be force times distance, which is also work. And that's why for potential energy you see this formula here. So notice that that's only divided by 1r because the other one divided out by multiplying the distance. So d or r, same thing. And the potential is voltage V, potential energy divided by charge. So if you take this one here divided by charge, you get just this one here, kq over r. We technically actually don't need this one here for the voltage, but just the potential energy. The result is already there in front of us. I can do it again. So let's see, that's from a previous one. So here we go, 9.00. Sometimes you see 8.99, and this one here is 10 to the 9th times, then in parentheses 1.6, 10 to the negative 19. That's the charge of a proton, and that would have to be squared, and then simply divide by the radius. I'm sorry, not the radius, but the distance between the two. So negative 12, there we go. And of course, that's the answer that's already written there, 2.30 times 10 to negative 16 joules. To put that into perspective, I looked up the following. I looked up the following. This one here. This one is in joules, which I just computed. This one here, let's say, would be for a hydrogen atom or any kind of other atom or nucleus, and the mass is in the neighborhood of 10 to the negative 27 kilograms. So it's 10 to the 11 times if you compare joules to kilograms. Not really, but let's assume I use 1 kilogram. Then for 1 kilogram, I have 10 to the 11 joules. So I'm looking at 100 billion joules, and here is 10 to the 11. So for example, 10 to the 10th kinetic energy of an Airbus, or the yield energy of this air blast bomb, the second most powerful non-nuclear weapon ever designed, or energy consumed by the average US automobile in the year 2000, or, I like this one, the approximate food energy consumed by an average human in an 80-year lifetime. And since this is just for 1 kilogram, as comparison, I'm 100 kilograms, so 100 people like me. And really what I'm doing here is just saying, okay, this is how much energy I would consume, or 100 people of me, and that is in relation my mass to the energy that we consume, as this one here is the mass of the proton or the atomic nucleus compared to the energy that they need to have in order to be close enough together. So kind of like in proportion. By the way, the force between them here, that would have to be divided by the distance again. So divide this by another 10 to the negative 12 meters, and so I would come up with 10 to the negative 4 newtons. Doesn't sound a whole lot, but again, if I kind of compare newtons to kilograms, again, it's kind of like not really the case. I would have 10 to the negative 4 compared to 10 to the negative 27. Again, that's the mass of a proton or an atomic nucleus or an atom. I have like 10 to the 23, so I looked that up too. So if I look up a force of in the neighborhood of 10 to the 23 newtons, I come up with the gravitational attraction between the Earth and the Sun here. And so in proportion, that's what we have here on a nuclear level. Of course, the mass is much, much smaller. Hence, the force is much, much smaller between them. But again, the ratio is just incredible. The force between them, the repulsive force is huge. The energy that they need in order to get that close together is just incredible. All right, let's do the second part of the problem, where it says, at what temperature will atoms of a gas have an average kinetic energy equal to this needed electrical potential energy? Well, again, they have this the solution here. So this is from the chapter on kinetic theory and thermodynamics. So the average kinetic energy, which would be this one here, that's the potential energy between them. So in order to get there, that's actually the energy that they would have to have in order to collide. So if I go here, if you picture them much further apart, they would have to really race against each other, a huge amount of kinetic energy. Then they're repelling each other, so they're slowing down until they come to the smallest possible distance between them, and that's where they have that potential energy. So all the kinetic energy has transferred into potential energy. And so this one here is therefore the kinetic energy. And so doing the calculation, I would take my 2.30 times 10 to the negative 16 joules, and I divide it by 3/2 in order to solve for temperature. And then I divide it by the, that one is the Boltzmann constant, right? So this K, by the way, is different from that K. This is the Coulomb constant, the 9 times 10 to the 9th. This is the Boltzmann constant, 1.38 10 to the negative 23rd. Looks like it's almost the reciprocal of the Avogadro's constant. The ideal gas constant goes in there as well. Enter, and of course I come up with the same result. They did 11 million kelvins. So that's how hot it has to be. In fact, when you look at any core temperature of a star, let's see which one it is. I think it's this one here. So I'm going to pull this up a little bit here. So here's the sun, and here is the core temperature. I saw it earlier. Where'd it go? Where'd it go? Should be. There it is. There it is. Temperature. Center. 1.57, so 15 million kelvins. So that indeed is the case. Let's see, I wanted to show a little bit more here. There's a little bit more to the story, actually. I'm going to show a couple other diagrams here. So this one here is actually the Coulomb repulsion as it's being described in the problem. But the scale down here is femtometer, which is yet 1,000 times smaller than the atometer that they gave us in the problem. So actually the two protons are way, way over here to the right. So they haven't even gotten this close here within 1 femtometer where they actually could fuse. They would have to have even more energy, and you could actually compute that you come up like with 1 billion kelvins, which is not the case. Stars are not that hot inside, but they are in the millions of kelvins. And so they need to do something else. They need to do what is called the tunnel effect, and I think they'd show that in this one here. So tunneling to higher energy. Here's again that 10 to the negative 15 femtometer, while the atometer at 10 to the negative 12 is way, way over here. But then it tunnels through, and that's a story for a later day, the chapters on modern physics, nuclear physics, in this case, the tunnel effect. Let's see, what do I have here? This one actually does talk about quantum tunneling in order to get there, where our sun keeps shining. One of many, many good videos about how the sun works inside this one here as well. How does fusion power the sun? I put the links in there. Let's see, I already looked at this one here. So yeah, this is where I got the diagram from for the nuclear fusion inside a nuclear reactor. And then this one here is the typical proton chain in a star, and there are other chains as well, like it says the C and O cycle. You can see that here. That depends on the star. All right, actually that's what I wanted to cover here. All right, and then I just have this one here for the lesser electric ray, and I think I just have you look at it right here respectively. This one will be available as well for the homework. And so this particular problem I get done in 20 seconds. Well, of course I always take a little longer, right? So let's see what I look up here. So here's the electric ray. Oops, that's not it. Okay, Joe finds out why it is called an electric ray. So someone, I let you watch this. You know, someone being zapped with quite some voltage. I'll let you watch this. Same thing on this one here. Anyway, Yep, done with this one. All right, the next few problems are about how to add capacitances in series and in parallel, and it mimics adding resistance in parallel and series, which, by the way, are more important. I'm totally used to doing that with resistances, and it turns out that in the lab with me, for example, you will be dealing more with resistances, and so when those are in series, you simply add them. When they're parallel, that's when you add the reciprocals, and then take the reciprocal at the end when you're done with that. For the capacitances, it's the other way around. Add the reciprocals when they're in series, simply add them when they're in parallel. So I actually have to get used to that because I don't do that on a regular basis. So, but I'm glad that OpenStax actually has this particular problem. Let me just point out here for the first problem that I want to do, which is number 57. So there it is. This is the original problem here. 10 microfarad and 2.5 microfarad in parallel, 0.3 microfarad then in series with those two that are in parallel. And you see that here, basically the same diagram. Actually, this one here from the solution, I do like that a little better because they put 10.0, 2.50, 0.300, indicating very strongly these are three significant figures. As I said, I like that better than the one you just saw from the original problem. So, in any case, so let me do it. The solution is actually in front of us. And so I'm going to pull in the calculator. Okay, I don't need this here, so I'll get rid of that. So, two capacitors in parallel right here, and which means I simply add them. So obviously 10 plus 2.5 is obviously 12.5, which is what they also come up with. And then I'm gonna do the other one in series here. So in series, the capacitance add as reciprocals. So I'm gonna do 1 divided by 12.5 plus 1 divided by 0.300. I don't really need that, but anyway, enter, and then I would take the reciprocal of that. And there it is, 0.2929, rounded to 0.293 microfarad, which is what they list here as the answer. Okay, a couple of things about this one is notice the answer of 0.293 is pretty close to this resistor C3 here. Well, that's because the reason behind that is that the resistors are widely different. This is a very small resistance. This one here is actually relative. I'm sorry, I hope I didn't say resistance all the time. I hope I said capacitance. Oh boy. So capacitance. So this capacitance is relatively small, 0.3 as compared to the other two here, which in parallel add up to 12.5. So when you do the reciprocals with that, the result from that, what is called the equivalent capacitance, there, I said it correctly, capacitance. So the equivalent capacitance is just a little bit smaller than the smaller one, because that's the way the reciprocals work. Notice that here I'm dividing by a large number into one, so I get a really small number to be added to the other one, and yeah, again, the result is 0.293. By the way, let me show you the last part again here with the 0.293. This is the way I actually do it quite often. I open the parentheses, I'm going to put the 12.5 here, and I do it to the -1. Okay, that's the alternative to 1 divided by 12.5 means the same thing, plus the other one, so 0.300 to the -1, close the parentheses, and now instead of hitting enter and getting that 3.41 that you see there as the intermediate result, I hit negative to -1 again, because that gives me yet again that reciprocal of that, and that's a quicker way of doing it. So 0.293. All right, let's go on to the next problem. I'm going to give myself a little break here. All right, scroll down. Okay, I sure hope I didn't say the word resistor too many times. Capacitance. capacitors. Okay, so actually, let me go back. I did forget one thing. So here you have to decide on any kind of these circuits which ones are truly in parallel and which ones are truly in series. And the way to do that is by the junctions. There's a junction right here separating this capacitor from the other two here, and we can definitely see that these two are in parallel, and that's why we had to start with this one. So these two are in parallel, and then those two being in parallel, they're in series with this one. So the next problem here, we can definitely see that the ones on the left are in series with each other, and then the one on the right here is in parallel with those being added toward the end. Okay, so I'm going to do the two on the left here to begin with. Actually, it's going to be, again, they're choosing here widely different capacitances here that I have to add as reciprocals in series. So I'm going to come up with something close to 0.30 again, which, you know, the solution is already there. Okay, I'm going to clear my calculator. So, as I said, parentheses 10.0. I actually don't need that, but well, to the -1, that's a reciprocal, plus 0.300, again the reciprocal, there we go, close the parentheses, and to save myself a step, to the reciprocal again here to -1, enter, and there is that 0.291 that they already listed here, and to that I simply add the 2.50 as they are in parallel with each other. And I am getting that 2.79 microfarads that they have. All right, again, I'm going to give myself a break here. All right, just catch my breath. Again, going back actually on this one here. So this was problem 60. Again, their diagram, they made a little bit more clear of giving us really 3 sig fig. You know, that's why I actually don't necessarily like this particular diagram. Same thing here. I think they're also going to give us 3 sig fig. All right, let's get going here. So here's the third one I'm going to do. Again, the solution is actually already here. Let's see. Let me look at it. Let me actually think about it. And so I'm going to give myself a break again. All right. Okay, and I'm glad I did that because I did notice that even though I like that they do 3 sig fig all the way through here, indicating it very nicely, but they did make a mistake in this particular diagram here in the solution. It's in the original problem. You see those vertical lines right here? There we go. Copy image. Maybe I'm able to put it in there. Let's see. In the meantime, oh, holy mackerel! Wow. Okay. So the circuit is such that you have an input from the top, so for example the positive part of the voltage source and negative at the bottom, but this is important here, that so it comes in from the top and then it goes out at the bottom. I'm gonna do this here so we can see everything at once. Gonna turn the light on in my office. Got dark all of the light switch has a motion sensor and it's kind of hidden, so I'm really sitting in my chair for a long time. The light goes off on me. Okay, so anyway, we can see as the wires coming in from the top and going out at the bottom that all of these here are pretty much in parallel, but we still have to pay a little bit of attention. So as they're all here in parallel left to right, but there is a little bit paying attention to. So the two on the left here are definitely in series with each other, right? Then the one in the middle here is kind of by itself. Then here on the right hand side, we have to pay a little attention. We cannot say, hey, this one is in series with this. First, we have to say that, hey, these two are in parallel with each other before we do anything. So these two are in parallel with each other, and then they're in series with that. And when I'm done with that, then all of the stuff over here is in parallel with this one and this one. Okay, let's start on the very left. These two are in series with each other. So, as capacitances, add as reciprocals when they're in series. So I'm going to have 5 to the -1 plus 3.5 to the negative 1. Again, I do appreciate that they put in the 5.00, but the calculator actually doesn't care. So I can write it like this, and then parentheses, and again to the negative 1, so I get the reciprocal. And 2.059, that's actually kind of what you see down here. So that's an intermediate result. So I have that one on the very left, 2.059. I have the 8 in the middle. Nothing happens there, so I just leave it there. I have these two here being in parallel with each other. Since they're in parallel, they simply add. So I'm going to do this. I simply add them in my head. 15 plus 0.750, so 15.75. Okay? These two here are purely in parallel with each other. Now these capacitances are in series with this one here, with the 1.50. So now they add as reciprocals. So to the negative 1 plus 1.5 to the negative 1, parentheses, and again to the negative 1, and it's 1.37, which is what they're listing right here. So that's the one on the right-hand side. The other result I had a moment ago are the one on the left-hand side. And then, of course, I still have the middle one, which I didn't do anything with. And now because now the stuff on the left and in the middle and on the right-hand side, they're all in parallel with each other. Capacitances simply add when they're in parallel. So I'm going to have the 2.0588 with a few more decimals here, plus the 8.0, so that was on the left, plus the 8.00 in the middle, plus the 1.369565. Sure, a little overkill, but that again, at least by doing that, I do get nice 3 sig fig. Enter, and now I'm going to round to the 3 sig fig, which is going to be 11.4 microfarad, which is exactly what they're listing here. All right, and those were the last problems in chapter 19 here from the OpenStax textbook. I think this is chapter 19. And actually, I recorded them first before I did the ones that are prior to that. Before I did, what is that? The one with the lesser electric rail, and this one with the fusion. So I'm going to actually do that next, probably in a couple of days, which you won't notice because it's one recording. All right.